The following content is provided under a Creative Commons license. Your support will help MIT OpenCourseware continue to offer high-quality educational resources for free. To make a donation or view additional materials from hundreds of MIT courses, visit MIT OpenCourseware at ocw.mit.edu.
So let's do a really fast estimation to just make sure you're up to speed on solar facts. So how big a solar panel do you need to power a 100-watt incandescent light bulb? Does anyone remember the flux, solar flux? Yeah, 1,000 watts per meter squared, exactly. And efficiency? 20%? 10, 20%? So to make it really easy, the math, let's go with 10. So that would be 100 watts per meter squared, and we have a 100-watt light bulb. So assuming there's no other inefficiency losses, and we're just going directly from solar panel to light bulb for lighting in the middle of the day, very common need. That would be a 1 meter panel, right? Or 1 meter square panel. Okay. So I think the solar options that we covered last week are SOTUS, and I didn't have time before class, but I'll try to hunt one down during the lab. An example of a SOTUS bag that a student invented that's kind of cool to see. Then there's solar thermal and PV. And so there was confusion about the difference between solar thermal and PV. So fundamentally, solar thermal is just using the greenhouse effect to get something hot and use that heat, as opposed to PV stands for photovoltaics, and that means you're taking the photons from the sun and converting that using a semiconductor material that has a photovoltaic behavior to get an electric current out from those photons. So that those are quite distinct, heat versus electricity. And so solar thermal is typically used for things like heating water, because it's really easy to heat the water, well, relatively easy to heat the water with the sun, and then it's just direct. So here's an example of, you have your panel, which is not a photovoltaic panel, but just a panel where you have a volume of water that's probably in a box that has black behind it, so you're maximizing your solar radiation. Your cold water goes in, the water heats up, your hot water comes out, and it goes into your hot water storage tank. There are, of course, many ways to make this much more complicated, so that you get different benefits, but that would be a simple way to think about it. And out in the Mojave Desert, there's a 350 megawatt peak output solar thermal installation. This is a little complicated because they're using the hot water, which is steam, to power a turbine, and that turbine creates electricity. So that's one way of getting electricity out of solar thermal, but it's indirect, unlike photovoltaics. So that's the distinction. And in terms of developing world applications, I hope I have some at the end, but if not, it's really common to, if you want a hot shower, to just have a big bag on your roof, and it heats up, and then you get hot water for as long as that bag lasts, and then it's cold water again. So that's one example that's common. And then I'll talk about some PV applications in a bit. So I wanted to do a quick overview of photovoltaics. So basically, again, the photovoltaic effect is being taken advantage of to generate electricity. This says in silicone. There's a lot of different photovoltaic materials I'll touch base on really fast. There's also confusion about what this junction is. The junction is emphasized because, on this slide, because it's where the interesting stuff happens in the cell, but it's just where the two slightly different layers of silicone interact generally. There's generally not a special separate material there, though this is complicated because we're generalizing, and there's a lot of different silicone and photovoltaic materials, and different ones behave differently. But generally, so I'm just going to talk about silicone, like a traditional silicone cell, because it's very common and easy. So you have silicone that on the top side has been doped in such a way that that's called N-type. So it means that it attracts more negative electrons. And the bottom side has been doped the opposite way, so it's attracting more, called P-type for positive, so it's attracting more positive electrons. And so you can imagine if negative, positive, you're creating flow. And that's critical because you need the flow in order to get the electricity out of the cell. So you can see here, you've got your N-type on top, your P-type on bottom. That's the junction where the positive electrons are going down, the negative electrons are going up, and we're getting electric flow, which is providing your electricity to light your light bulb or whatever you want. Yeah, so you can sort of think of this as a diode, right? Because it's allowing directional flow, like we talked about, like a light emitting diode. It's just an electricity emitting diode is one way maybe of thinking about it. So there's a bunch of different materials. Yeah.
Wait, so are you saying, wait, the N-type, it attracts negative, or it is negative, so it attracts positive?
So the, can I remember this? The N-type has more, you know what, I can't even remember, because, so it's not critical. There's a difference, they flow. Does anyone remember?
The N-type is got more electrons in it.
Yeah, the
It's a
N-type.
negative material.
Thanks. So, yeah. Okay, so the efficiency is really going to vary depending on the material and how carefully it was processed, and carefully translates to cost. And the other thing to remember is that it's dependent on light normal or perpendicular to the surface, so that's why you have to tilt your solar panels into the sun, and why some arrays that are expensive automatically tilt themselves. Other ones you just put on the house or wherever you're putting it at the maximum angle for the most amount of time. But if you don't put it in the right place or the right angle, you're really going to minimize the efficacy of the cell. Someone wanted to know, is it just silicone that's used? No, silicone is most popular right now, but you can see there are some other materials, some of which are more experimental than others, and I'm sure there's additional examples that I don't even have on here, but there's a lot of different materials used, all of the pros and cons. For example, cadmium is pretty toxic if it gets out, but hopefully it doesn't, but it's all challenging. So how solar, or how, yeah, sorry.
So you use silicon because it's a good semiconductor?
Yeah, yeah, and exactly. So silicon's a good semiconductor, and a semiconductor means it's not a full conductor like, say, a copper wire, and it's not a full insulator like, say, the plastic around your copper wire. It somewhat conducts, and that allows you to do cool things like having the photovoltaic effect.
So that wouldn't work if it was completely, like a complete conductor?
Well, complete conductors don't have a photovoltaic effect.
Okay.
I think is a good way to think about it. Do you disagree?
There's
I think you might be able to, like, make excite electrons and stuff, but I don't think you can't, like, dope them to create that.
Right, exactly. So
There's no
distance it
energy
makes
gap.
possible.
yeah, all right, thank you for helping me. So the clarification is that the semiconductor allows you to have create flow, so that when you excite the electrons in a material, they have to go somewhere in order to be useful, right? And if it's fully conductive, you can't change. Remember how we talked about, so this is doped differently than this, so you have a negative side and a positive side to allow for flow. You couldn't do that in a full conductor, but you can in a semiconductor. So. Come on, little laptop. Okay. So photovoltaics is generally wiring a bunch of solar cells together. You guys wired in series, I believe, but they're typically wired in series and parallel, and I'll get into that in just a sec. And then you can take those panels and wire them together into big, enormous systems. And one of the things that's been challenging is that they're sensitive to temperature. And so, for example, in areas where it's really hot, where there's a lot of sun, that'd be a great place to put a solar panel, except they get too hot and then they get less efficient. So they're really frustrating. There were some questions on series versus parallel wiring, and hopefully this is just a quick review. But if you put two cells in series, the voltage is additive. And so we have two 6-volt, 350 amp hour cells, you put them together and you're getting 12 volts. Whereas if you wire them in parallel, the voltage isn't additive, the current is. And if you put them in series and parallel, which is how they're commonly wired, then you get the voltage and the current you actually need, ideally. However, the thing to always remember with solar cells, which hopefully you'll notice today, is that if you cover one of the panels up, that drops the current in that panel, and it affects all the panels when they're wired in series. And so it's a really frustrating reality that they all need to be equally clear. So the components of a solar system, you have a panel, you have the regulator, which typically has the components inside it so that you make sure that the electricity is flowing in just one direction, as we talked about. It goes to some sort of storage, and then it goes to an inverter if you need AC appliances. You can see that all of these different components have efficiencies, so every single one is going to drop your afraid to click too many times, is going to drop your efficiency, which is really frustrating. So again, you have grid-tied systems, just like we've had in everything else, or you have standalone, or you have hybrid. I'm not going to talk about grid because we don't do that much in this class. But for standalone systems, so you have your charge controller going to your battery and then an inverter. So just what we talked about. And I don't know why today is going so poorly, but it really is. I'm sorry. Yeah.
So for like solar cell phone charger, you would need not only like some resistance to get the total resistance right, but you'd also need that inverter.
So hypothetically, yeah. People do all sorts of bad practices and get away with it for better or for worse. So for example, the battery charger I showed from Phoenix on Wednesday is literally just a panel with a couple of wires coming out, going into a place where you can charge your batteries, which means that it has great possibility for failure, but it's really cheap. And so there's always that trade-off of you can take something and it'll be super cheap, and that's handy, but it won't work very well, and you have to figure out what you want, right? Like you can make this a $10 million, that'd be hard, but you know, $1,000 system or a $1 system, and there's real trade-offs in terms of cost and performance.
But it still works as direct current?
Well, so batteries only need direct current,
okay,
so
okay.
they're getting direct current, whereas like this computer's expecting alternating current, so I'd need a special device if I wanted to use direct current. This computer's a bad example because of the cube that actually does take direct current too. But this projector would need a special device to get direct current. And so, of course, you can see extremes from a standalone system in Bangladesh all the way to a 10 megawatt solar array. So this is at in Abu Dhabi. Yeah. So I don't want to take the time to go through this whole question, but it'll be in the lecture notes that I'll post today. So if you, and I think I'll post them in week 4 because this was the solar lecture that never was, but it makes sense to put in the solar week. But if you can go through it, this actually walks you through it, but I'd recommend doing it like we do in class. So try to do it, and then if you get stuck, you can go through it. But this is good practice, especially because the homework has been dying out in order to make sure you guys have enough time to get all the work done. But this is a helpful calculation to be able to do. So developing world applications. Just quickly, what do you think people tend to use solar for in developing countries?
Water heaters.
Water heaters? What else? Yep. Yeah, so TV is asking a lot out of a solar panel. You might see it, but it's going to be expensive. And you certainly wouldn't see like a refrigerator on here because, again, that's getting really expensive in terms of the size of the panel you need. And some examples that we've talked about, but I just wanted to refresh your memory on. So one is Grameen Shakti in Bangladesh, where women wire up the solar panels. They use microfinancing to make the panels affordable. They're often in little markets where people buy little amounts of food and things like that. They can also access electricity, or the market can just have light on at night. And they also do micro utilities too. I believe there's about 1,000 micro utilities operating in Bangladesh. I'm not sure how they pronounce themselves, but this group in Brazil, and they do a fee for service where the company is responsible for the care of the battery, which is critical because batteries require care, and if they're not well cared for, you can cut their life by half, if not more, and they're a pretty expensive part of the system. They work on a flexible payment system so that the customer decides, because some people work in areas where you might make most of your money in 1 month. And so if you're expected to pay month by month, that can be really tough, but if you can just pay once a year, it works. And then they do a lot of user education to help make sure people use them effectively and care for them properly. Selco we also talked about in India, and they have lots of different examples, from lighting in a temple, storing cocoons for silk industry, in houses and marketplaces. We talked about D-Light Design, and they have lights that come with a solar panel or have the solar panel integrated into the light, so people have a light option even if they don't have a home installation. One of the challenges with solar like this, and you'll see it a lot, people have it on their bags, or you can buy a charger or solar panel that you can put wherever, is it requires you to be outside, or it to be outside, and so it's challenging. Like, I have a flashlight that has a solar panel on it, and I stopped bringing it on my field work because I'm not necessarily outside the whole day, and I can't just leave it there or else it'll walk if I don't keep an eye on it. And that's true for everyone. And so that's one of the frustrating things about solar generally, is that the panel is expensive and worth something, whether it's integrated into the device or not. And so figuring out how you keep the panel secure, it's easy to stick a battery inside a secure room, not so easy to stick a panel inside a secure room that has no roof. So that's challenging. And they tend to be small enough that they're easier to steal than, say, like a wind turbine or something like that. The Solar Thermal Group, which is an MIT project, this is an example of using solar thermal in a developing country. And they have a wide variety of applications of different ways that they use the solar thermal, but some of which I think is electricity generating as well from the steam. So that does have a real world application.